Hello, everyone. As usual, I start with your questions. Do you have any questions about the homework I assigned before we get started?
Yes,
if you have any of them, please put your question on the chat. We look at them and then we proceed. And if I don't get any questions, I usually keep going. No, I cannot do that. You have to pick your problem. Usually you pick your problem. I don't pick, you pick. So give it your best shot, Emma. Okay. Yes, question 26, and we do that. So you have to be precise in your questions. Did I assign 26? I think. All right. And I imagine that section 1.3. 1.3. Okay. So 26, we have A to be the following set. Sorry, A to be the following matrix. 2 minus 1, 1. Okay, and 0, 8 minus 2. 6, 5, 1. And I have a vector B, which is 10, 3, 3. And W, so something called W, and W is the set of or linear combination of the columns of A. So what do they mean by that? What do they mean linear combination of the column of A? That's what they mean by columns of A. So let me call this V1. This is the column of A, let's call this V2. And this is the column of A, we call this V3. So W is all possible linear combination of those. This is another way to say that W is the span of V1, V2, V3. So W is the span, or W is all linear combination of V1, V2, V3. So that's what they mean by the columns of A. These are the columns of A. And the question is B in W? Is B in W? What does this mean? It means is B a linear combination of V1, V2, V3? So is B in W? It means can I write it? So the question is basically, can we find C1, C2, C3, or X1, X2, and 3, such that if I put a little bit on V1, some weight on V2, I stretch V1, and I put some weight on V3, I could reach the vector B. So that's really what their question is. And now the idea is usually the same idea. I need to solve the system. So I've been always doing it by rewriting it very carefully, so you know exactly what we're looking for. And the question, can I do that? So equal to that, 10, 3, 3. And that's it then. Otherwise, I write it 16. So this is really boiling down to solve the following system. So if I equate the vector here by combining and equate this vector, this really boils down to solve the system where the augmented matrix is that. And we're solving for the weight. These are my unknown in here. So that's really what this problem is about. So the question is, I have to take this and I need to reduce it, okay? And usually I don't reduce every matrix in class anymore because it's really wasting a lot of my time and yours. So I will do the first step, and then if any of you has done it, please give me the echelon form because I will not reduce anymore. But I do the first step. If I am doing this problem, I probably bring the 1 here first to make life simpler. So -2, 1. So that's what I will start with. And then -1, 8, 5, 3, 2, 0, 6, 8. And now I reduce to see if I can find a solution or not. Okay, did anybody do that? Did anybody reduce it? That should be a 4. That should be a 6. That should be a 6. I'm just adding. And then I'll have -2 plus 2. I'll have -2. Let's give me my 4.
Shouldn't that 4 be a 6 in the second row, or am I wrong?
1 minus 1.
Yeah,
right?
that's 0, and then
That's
-2
6.
plus, yeah.
Yeah. Okay, and then I will have -2 plus 2, and that's going to give me correct. And that's going to give me -2 plus 6, which is a 4, correct? And finally, I'm going to get here -6 plus 10, -6 plus 10, that's going to give me a 4. Okay, so this will give me the following. So this turns out to be simple. 1 minus 2, 1, 3, 0. I divide by 1 immediately because it's 6. I don't want to deal with it. And this seems to be very easy. 0, 1, 1. Now, of course, I am not in echelon form. I have to get to the echelon form. Otherwise, it doesn't really work. So let me get to the echelon form. We don't stop till we get there. 1 minus 2, 1, 3, 0, 1, 1, 1, 0, 0, 0, 0. Okay, so we get there. So what does this mean? What does this mean? Is B a linear combination? So what does this mean? The system is consistent, correct? Which means that I can find a solution. There is no question about. And what else? We can find a solution, there is no problem. But I don't know if this bothered you, but it may have. But this tells me there are infinitely many solutions. What does this mean, infinitely many solutions? It means I can write B as a combination of those vectors, but not in one way, a lot of ways to write it. That's really what it means. So having infinitely many solutions, it means there are different ways to write B as a combination of V1, V2, and V3. So let us proceed a little bit further to clarify this idea. So if I'm solving this, definitely my C3 can take any value I want. My C2 is totally constrained, is 1 minus the C3. And my C1 is constrained. It's 3 plus 2, C2, but the C2 is that, minus C3. So it means it's going to be equal to 5 minus 2 minus C3. So what does it mean to you? So as far as we are concerned, yes, B is in a linear combination. This tells me, the infinitely many tells me there are several ways of writing it. So for example, if I take C3 to be 0, C2 will be 1, and C1 will be 5. This tells me if I take 5 V1 plus V2, I should be able to get my vector B. You can check the math. And this time, you know, that's not the only way you can do that. If you take C3 to 1, then C2 will be 0, and C1 would be 5 minus will be 2. It means also, if you take 2V1, that's what it tells me, and V3, you can also get a B. So you can get a B as a combination, not in only one way, in different way. And that's the meaning of infinitely many solutions in this particular scenario. Now let me look at question B here in the same problem. Not any questions before I proceed. So let me look at B. B tells me the following. Show that the third column of A, it means V3 is in W. Okay. So W is the span of V1, V2, and V3. That's what W is. So now my question, the question is actually, is V3 in V1? Or show that V3 is in W. Okay. How can I show that V3 in W? How can I write it? I'll answer this question in a minute, Chris. So show V3 in W. How can I write V3 as a combination of V1, V2, and V3? That's what it means to be in W. Can I write V3 as a combination of those? And what is the weight? Quickly. So is W in the span? It means, is this in the span? It means, can I write it? Yes. I put 0 for here. I put 0 for here. And I put 1 for here. So of course V3 is in the span because it's 0 V1 plus 0 V2 plus 1 V3. End of the problem. Now one of our classmates, it tells me, if the system had a unique solution, that means the vector equation cannot be scaled. Yes, it is. The scalar, if it have unique solution, then this unique solution will be the weight. So instead of having several ways of writing it, B as a combination, I will have one way. Not two, I will have one way. So unique solution means you have a unique way to write B as a combination of V1, V2, and V3. Infinitely means you have a lot of them. Okay? Inconsistent means they cannot be scaled. Inconsistent means that we cannot scale the V's to reach the vector B. That's when we cannot do it. Right. Okay, I'll take up one more question. If we have time, can we go number 21? 1.3, so I'll look at number 21 very quickly. What is it about? Okay, 21 is the following. I have the vector u, which is 2 minus 1. And v, so this is very much a problem I did last time, 2, 1. Okay, so those are two vectors in R2 here. It means in R2, it means they have basically two components. So 2 minus 1, so it's a 2 and a minus 1. And 2, 1, 2 and 1. So this is my U and this is my V. You don't have always to sketch, but I'm sketching for so you can imagine. And the question that if I take any vector, so show that HK is a vector. So show HK is in the span of UV, no matter what H and K is. So here the question they're asking you that this is U and this is V. So geometrically, of course, we're going to do the problem algebraically. The geometrically is this. Pick any vector HK anywhere here. Suppose it's HK here. And the question is show that this vector is in the span of UV. We basically show that you can really get to vector HK by really going a little bit in this direction and then in this direction, which is algebraic, geometrically we can. Now we're going to prove it algebraically. Okay. So let's do that. So it means we have to show that. This is HK. No matter what the HK here, I have to show that I can put weight on U and V. That's what we have to show. We have to show that this equation, this vector equation, has a solution. It means the system is consistent regardless of what H and K is. That's really what we have to show, okay? So basically we have to solve the system and convince you that we always have a solution. So let us solve this system. One way to do those is basically solving and going to the echelon form. So solving this system is basically solving that. If I combine, I will get 2C1 plus 2C2H minus C1 plus C2K. So it means I need to show that this system has a solution regardless what kind of anything I put here does not affect the solution. So I take, the only way we solve this is to go to the echelon form and then discuss and then look at it. So this is going to be 2 minus 1, 2, 1, HK. I need to reduce. So as I said, it's easy for me to have the 1 in the first row. So I'm going to multiply this row by negative and move it up here. And this one I keep it 2. Okay, for me that's easy because I avoid fraction. So finally, this will give me the following.
Would K be negative?
Thank you very much. Now, minus 2 plus 2, so this is minus 1, minus K, and then let's see, minus 2 plus 2, it's a 0. And minus 2, that's give me a 4. And then minus 2, that's a K, give me 2K plus H. Okay, so I will write it clearer here. So 1, 0, minus 1, 4, minus K, and 2K plus H. Okay, now the question is, that's the echelon form. And the question is that, can I always solve for the weight C1 and C2? Regardless what H and K are, can I always find the solution? Yes or no? It means whatever I put, I mean, even if I put here pi for K, and what's another nice number here? If I put E for H, no matter what I put, can I always solve for C1 and C2? Okay. And the answer is yes. The system is consistent. So regardless, so this is consistent. Why it's consistent? Because there is no way, because there is no row that has the following form. 0, 0. I cannot have this row because I have 0 leading. So I have a leading in this row. I have a leading in this row. And the leading is not at all in the last column. The leading is in the coefficient part of the matrix. I have a leading here and I have a leading here. There is none in here. So because no row of this form. So the system is absolutely a consistent system. And if you just think about it logically, I can actually solve because this will give me 4C2 is to K plus H. It means I can solve easily for C2. If I know C2, I can back up and solve easily for C1. It means I can find the weight. All right, so this tells me that every vector in AR2 is in the span, which expressed the idea that we talked about last time. It means the span of U and V is equal to R2. Meaning every vector here, it means every 2 by 1 matrix. Every 2 by 1 matrix. That's what R2 is. All the 2 by 1 matrix could be written as a scalar times this plus a scalar times that. End of the problem. Okay. Okay, so with this, I answer your questions. And 1.3, number 7, I can just listen to the lecture of last time. We did almost the same problem there, so please listen to it. Any questions which is that you still help you understand the ideas better? So today we are going to move on to section 1.4, matrix equation. Okay. So what's the idea of matrix equation? So the matrix equation AX equal to B. So this section is actually a new notation, a new operation on matrix, which is gonna explain two things: why we wanna represent solutions as vectors, not only as a list of numbers between parentheses, why we insisted on that. And we're gonna start emphasizing the coefficient matrix, not only the augmented matrix. So I start with a definition first. So matrix equation, AX equal to B. First, product of a matrix and a vector. So we're going to define something new called the product of a matrix and a vector. What does it mean to multiply a matrix by a vector? So let A be a M by N matrix. Remember, M represents the number of rows. And this is the number of columns. That's what it is. Okay. X, a vector in Rn. It means X has n component. That's what it is. X in Rn, it means X has n component. And let A be A1, A2, An. So what do I mean by this? Where each AI is a vector in Rn. Let me explain this very, very clearly. It means, suppose, then I take back 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If this is my A, so by A1, I mean this vector. By A2, I mean this vector. By A3, this one. By A4, this vector. So when I'm writing this notation, A is A1, A2 through An, it means these are the vector I'm thinking of. This is here, that's a 3 by 4 matrix. And each one of those, because we have 3 rows, have 3 entries. It means each one of those is in R3 just because it has 3 entries. Each one of those in R3, each one of those in R3, and so on and so forth. So that's really what I mean by the vector, by A1, A2 through An. And X, a vector in Rn, it means just a vector that has n component. Now we're going to define what do we mean by A times X. A times X means A1 through An times X1, Xn. That's the definition of it. It's equal to. Basically, it's a linear combination of the columns of A where the weight are X1, X2. So what does the definition? So that's the definition that we're learning. So it's X1, A1 plus X2, A2 plus Xn, An. So it means that it's X1, the first entry of X times column 1 plus X2, column 2, X3, column 3, and so on and so forth. So A times X is defined to be the linear combination of the columns of A, where the weight of the linear combination are the entries of the vector X. So A times X is a combination of those vectors. These are the weight. The entries of X is the weight. Now, since it's a linear combination of vectors, it means A times X itself is a vector because we're just combining vectors. So that's the definition of the product of a matrix and a vector. So quickly an example to understand this definition. So this is an example. Suppose A is the following matrix and X is the vector 2, 4, 1. So in this problem, this is my A1 and this is my A2 and this is my A3. That's really what it is. X is the vector with entry 2, 4, 1. So what is the X? A times X. A times X is verbatim. So A times X. That's the definition. That's how we define this. Is equal to. It's a linear combination of the column of A. So these are the column. It's a linear combination. But the weight are the entries of the vector X. So it's 2 times that plus 4 times minus 1, 1 plus 1 times 2, 4. So that's the definition for the product of a matrix and a vector. Now we just compute it. It's just a vector. We're adding vectors in R2 and scaling them. We are going to get a vector in R2. So the vector is going to be 2 minus 4 minus 2 plus 2, which is a 0. Then it's a 6 plus 4 plus 4, which is going to give me 14. Okay, so the product of a matrix and a vector is a vector, which is a linear combination of the columns of A. Now, example number 2. Suppose a vector V is 3 times 1, 2, 4, 5. So it's a vector plus 6 times minus 1, 2, 4, 1. Okay, so let us note here that V is in, since it has 4 components, that's what we say it is in R4. It means R4 is everything, all the vectors have 4 components. So V is in R4. Now the question is simple. I want to go backward. I want you to write V as the product of a matrix and a vector. So we have to write it as a product of a matrix and a vector. So V, I want it to be the product of a matrix and a vector. What is the matrix and what is the vector? So what is the matrix according to our definition? The matrix is, these are the columns of the matrix. So it's 1, 2, 4, 5, minus 1, 2, 4, 1. So that's the definition. That's the definition, nothing more than that. And that's the vector. So that's the A, that's my matrix A, times my vector. Okay, so that's the matrix and that's the vector. Right, so we try to go back and forth between them. A times X is defined as a linear combination of the column vectors. So now if I give you a vector which is a linear combination, I'm asking you to rewrite it as the product of a matrix and a vector, so we can understand the definition backward forward. Now, comment. Can I multiply any matrix by any vector? Or is there a restriction on the sizes that we can talk about? So what I mean by that is the following. Okay, so what I'm talking about is actually the following. When is A times X defined? So when is A times X defined? It means when can I multiply a matrix by a vector? Under what condition? Watch how the definition is done. The definition is done. A times X is the linear combination of those, which means that to be able to do this, the number of entries of the vector X should be equal to the number of columns of A. Otherwise, it doesn't really make sense or whatsoever. It means if I have here 4 entries, the problem doesn't make sense because it's 2 times this plus 4 times that, plus 1 times this. So fourth entry make no sense whatsoever. So A times X is defined if the number of columns of A, the number of columns of A equal to the number of entries of X. So to be able to multiply a matrix by a vector, this condition has to be satisfied. So here's an example, a question basically. Suppose A is 5 by 6. Then for A times X to be defined, X should be in R what? Okay, so ask my question again. So if A is 5 by 6, okay, A is 5 by 6. It means A is 5 rows and 6. It means 6 columns. 1, 2, 3, 4, 5, 6. And my question is that A times X makes sense. So when I multiply them, I should get something. My question is, this vector, how many components should it have for A times X to make sense?
5.
No.
6, sorry, 6 columns.
It should be absolutely 6. It should be the number of columns of the matrix A. So I can do this piece. So I can start adding the linear combination. So when we're multiplying a matrix by a vector, we have to be very careful of the picture. Now, there is an equivalent definition of the product of a matrix and a vector that's called the row column definition. So we're going to define the product in 2 ways. We've already, the main definition is as a linear combination, but there is another one which is easier sometimes to actually use it by hand. So for this, I'm going to show you by example how we do it, and then explain it a little bit more. So suppose I take the following matrix. So I will not make things hard. -2, 4, and let me take 3 and 7. And I'm going to multiply it with a vector because I have 3 columns. I need to multiply it with the vectors with 3 entries. So what is the definition verbatim? I will follow it. So these are my columns now. The definition tells me it's x1 times 1, 2 plus x2 times -2, 4 plus x3 times 3, 7. That's the definition as a linear combination. Now I'm going to add those together. So far I'm not really doing much. I'm going to add them. What would I get? x1 minus 2 x2 plus 3 x3. That would be the first entry. I'm just adding vectors. Now it's going to be the second entry. 2x1 plus 4x2 plus 7x3. Okay, so far I honestly didn't do anything. That's the definition. And that's really nothing more than adding vectors, scaling vectors, and then adding them. But now I'm going to show you how can we get this in another way than doing this. Just another way. Watch how I'm going to do to get the first one. So it's what we did is we took x1, and then basically we took minus 2x2 plus 3x3. Means I basically took this row here. That's where the word row is going to come. And I took this column, x1. And what I did, like something like the dot product, I took x1 minus 2x2 plus 3x3. That's the first component. Now, what's the second component? Again, I took this row and I multiplied basically term by term. 2x1 plus 4x2 plus 7x3. 2x1 plus 4x2 plus 7x3. So that's really just a different way to compute the product. It doesn't really give me a meaning for it. The meaning of the multiplication is right there. But sometimes you're doing something by hand. I don't care about the meaning. We can do what's called the row-column definition. Okay, so this is called the linear combination definition, and doing it row-column called the row-column definition. So to practice this, let us do a problem in two ways. One using the row-column definition and one using the linear combination definition. So let me take the following simple problem. Suppose I take the following matrix. I'm just make up number, nothing really deep. 1, 2, 3, 4, 5, 6. And I'm going to multiply it. Because I have two columns, I need to multiply it only by two numbers. So let me multiply it by -2 and 1, because I don't want hard number. I'm going to do the multiplication now in two ways. I'm going to do the multiplication as linear combination. And then I'm going to do the multiplication using the row column. So all of us will know exactly. Oh, as a linear combination, it's -2, so those are the weight, 1, 2, 3, plus 1, 4, 5, 6. Now, if I add those, granting I do some stupid mistake, I will get 2 here, -4 plus 5, -6 plus 6, 0. That's as a linear combination. Now row column. What we get? Okay, now I'll do it with you. -2 plus 4. That's the row, that's the column. So it's -2 times 1 plus 4 times 1. Here, -2 times 2 plus 5 times 1. That's the row column. And this is 3 times -2 plus 6. Now, of course, we're doing the same thing, but in a different way. So this is going to give me a 1, and this would give me a 2. Okay. All right. Now, why we're introducing this? Of course, there is a reason behind that. We're going to start basically writing the system in a slightly different way. But before I do it, let me talk a little bit about, get ready the language. The matrix equation AX equal to B. Okay, suppose I ask you the following very intuitive question. Suppose A is the following matrix. The one, I give it to you. X is the following vector. And B is the vector 1, 3, -1. And my question is X, is this vector X, a solution to the matrix equation AX equal to B? So remember, back in middle school, or I don't know, elementary school, if they give you a simple equation, like 2x equal to 3, and they ask you, which is basically, that's the general format of that. If I ask you, is x equal, I don't know, 4 a solution? You just plug in here and you see if it's satisfied, and you tell me, no, it's not a solution. That's really basically the same idea. Now that we introduced the meaning of the product, is x a solution of the matrix equation? And now why it's called matrix equation? Because that's inequality, that's an equation. Matrix because it involved basically the matrix A. So is x a solution? Big deal. I take A, I multiply it by x, and ask myself, do I get the vector 0? Pure and simple. Now, how you want to multiply them in this case, I don't personally care, because I'm just asking you, when you multiply them, do you get B? So I multiply, I get it. So 2 minus 2, right? 2, row, column, 2 minus 2. Sorry. Okay, that's going to give me a 0. So do I need to go any further? 2, 4, plus 2, 6, minus 3, that's a 3. And then 6 plus 5, 11, minus 8. Give me a 3. So is X a solution? Definitely in this case, no, simply because when I took A, multiplied by X, I did not get the vector B. Okay. Now, example number 2. So here I just ask you is a solution. Now, the following example. Suppose I give you a matrix A and a vector B. And now the question is, solve the matrix equation AX equal to B. What does this mean? Solve the matrix equation X equal to B. This time, and write the solution as a vector. This time, I'm asking you to find the vector such that A times X equal to B. So let us fully understand it. It means I need to find the vector X such that when I multiply it by A, I get the vector B. So this is my A. Minus 3, 6. This is my B. And now I'm asking for the vector X. Now, the vector X, I did not tell you how many components does it have on purpose. Because if I want to multiply it by X, my vector X will have to have 3 components. So solve the matrix equation AX equal to B is nothing more than find the vector such that A times this equal to B. Now we just have to go to the definition. So whenever you have something like this, a definition, okay, what does it mean this equal to that? Now you have 2 different definitions for the product. You can use either one to set up your problem. So one way, 2, 0, 24. So this means that you have x1 plus x2 minus x3. I'm using the row column. You can use the other one. It doesn't matter. x1 plus x2 minus x3 is 2. x1. So, and very soon this will become very, understand the picture. And then this is becoming 2x1 plus x2 plus 6x3 equal to that. So solve Ax equal to B. I go through my definition. I use the row column because I want to do it quickly. It means you set this equal to that. So it means basically we have to solve a system. This is the system. Plus 2x2 minus 3x3 equal to 0. So this section is really about terminology. There are not much concept in it actually. Equal to 24. But what does it mean to solve a system? What does this mean? So we have to take the augmented matrix and solve it. So we take the augmented matrix. And what's going to be the augmented matrix? So the augmented matrix is going to be 1, minus 1, 2, 1, 2, minus 3, 0, 2, 1, 6, 24. So what is the augmented matrix? This is nothing more than A, and this is nothing more than the vector B. So the augmented matrix is nothing more than AB. So solving Ax equal to B, it means find the vector X. When you multiply it by A, get the vector B. Really boils down to solve this system where the augmented matrix is AB. Okay, so solving that is actually solving that system. So now we just have to solve a system, which is we done, I think, several times. So let us do that very quickly. Okay. So this is gonna give me the following. 1, 1, minus 1, 2, minus 1 plus 1 is 0, minus 1 plus 2, it's a 1. I multiply this by minus, it's a 1, minus 3 minus 2, and this will give me minus 2. Minus 2 plus 2, it's a 0. Minus 2 plus 1, it's a minus 1. And then I multiply this by minus 2. minus minus a plus, 2 plus 6, it's in 8. I multiply this by minus 2, give me minus 4, and this is gonna give me a 20. Okay, we're just solving, and then we're gonna write the solution as a vector. Okay, so I have to go one more step. A 1, 1, minus 1, a 2. 0, 1, minus 2, minus 2. 0, I add them. That's gonna give me a 0. I add them. That's gonna give me a 6. I add them. That would give me an 18. So now I'm going to solve. So let us solve. The last one, read 6x3 equal 18. It means x3 is 3. Easy. This one would read the one before it. I'm doing a simple back substitution, and I know I have one solution because there is no room for a free variable in this particular problem. So x2 equal minus 2 plus 2x3. So it means that x2 is minus 2 plus 2 times 3, that's a 6, equal to 4. And finally, my x1, it's 2 minus x2 plus x3, which was giving me a 2 minus 4 plus 3, which give me a 1. Okay, so it means my x, and definitely a vector notation because I am solving a times x equal to b, means I want this x written as a vector. So my x would be 1, 4, and 3. Okay. So let us sum up what we did, because it's fairly simple, is what we've been doing, but with a different notation involved, nothing really deeper than that. So this means now if I take the matrix A, times it by x, I should get the vector b. So let us sum up that a little bit. What does it mean to solve the matrix Ax equal to b? Solving it means equivalent to solve the system with augmented matrix AB. So whenever I tell you solve Ax equal to b, it means basically solve the system with augmented matrix AB. So that's what this means. Now I'm going to do something vice versa. Every system, now we're going to start rewriting it. Every system, we're going to start rewriting it in the form Ax equal to b. And that's going to be like the standard form of writing the system a lot of time. So what I am trying to say, suppose I have the following system, simple system. My question to you is, find a matrix A and a vector B, such that solving the system is equivalent to solve Ax equal to b. The reason being, a lot of time, we start with the system, not in my class, in any of your other classes, they take the system and they will rewrite it in this format. And that's crucial for us to see where everything is coming from. So what's gonna be the A and what's gonna be the B, so that solving this is really like solving that. So A always is the coefficient matrix. And B is the vector whose entries are the constant term. So in other words, what's the A and what's the B? The A is the following matrix. 1, 1, 3, the coefficient. And then it's minus 2, 1, minus 3. So A is the coefficient matrix. B is the vector 2, 4. And if I consider the system, find a matrix such that solving this is equivalent to solve Ax equal to b, it means that solving this system is really equivalent to solve the following matrix. A times x equal to b. It means 1, minus 2, 1, 1, 3, minus 3, x1, x2, 2, and 4. Okay, so since now on, in this class, in a lot of other classes actually, instead of telling you solve the system and writing the system in this format, they tell you solve the vector, the matrix equation A times X equal to B. So it's actually a different way of writing this kind of system. Now, one more idea I would like to emphasize before we take the quiz, which is the following. I'm gonna go back to a previous problem, and I'm going to add a question to it. So I'm going to go back to the following problem, and I'm going to add a simple, not a simple question, but I want the idea to start sinking in. So I took up the following example. Let A be 1, 1, 2, 1, 2, 1, minus 1, minus 3, 6, and B the vector. And I told you the following. Solve the matrix equation Ax equal to B. It means find the vector that when you take A, you multiply it by it, you get 2, 0, 24. So we did this work by using the definition of the multiplication in the row column. And when we did the work, we got X equal 143. Now I'm going to ask you the following question. I'm still working with this matrix A. So I will just emphasize it by itself now. Okay, this is my matrix A. And now I'm going to ask you the following question, and that's the solution. Write the vector B as a linear combination of the column of A. Okay. Write B as a linear combination of the columns of A. So I know it's a lot of things to hold at once, but you will get there. So why I am allowing myself to ask you this question right after we solve? Because when we solve for X in here, it means what I showed you, that if I take the matrix A and multiplied it by the vector 1, 4, 3, I got the vector 2, 0, 24, which is the vector B. So if I took 1, 1, 2, 1, 2, 1, minus 1, minus 3, 6, and I multiply it by 1, 4, 3, I should get to 0, 24. Now I'm asking you, can you write B as a linear combination of the columns of A? Can I do that? And is it easy? Okay. We know that there are two definitions of the multiplication. Either you do the row column or the linear combination. So if I use the definition of the product as a linear combination, I'm going to get the vector B to be equal to the following. 1 times 1, 1, 2, plus 4 times 1, 2, 1, plus 3 times minus 1, minus 3, 6. So I solved first, and then the goal of B is really to emphasize the idea that when you are solving Ax equal to B, that those solutions, the 1, 4, minus 3, can be viewed as the weight that you put on those columns to give you the vector B. Okay. So this section is, as I said, it's a new notation, which is the product of matrix and the vector, that we will be using starting today, actually, to write a system. So instead of writing a system this way, we're going to actually start moving and writing it as ax equal to b. And this will be one of the main reasons I want us to see all my solution as vectors, not really only as ordered as like a list of numbers between parentheses. I need to see them as vectors because we need to multiply them with matrices and work with them. All right, I'll finish this section at this note, and I will assign problems for next time. So I'll give you enough time for you guys to take your quiz. So as usual, you can go to the content area, hit on quizzes, and your quiz should be, as usual, in the content area. So I will check with you, and it should be open by now. Yeah. Okay, so the quiz is there, so please get started. The first problem, I basically gave you everything. It's very simple, so good luck. If you have questions, you can send them on chat.